Hi, my name is Kalavani Subramaniam. My group member name is Buruntanika Tamilmaran. Today we are going to explain on thermal properties. Me myself going to explain on specific heat capacity and specific latent heat. My friend going to explain on equilibrium temperature.
You might have noticed that if you're trying to boil a lot of water, it takes longer than if you only wish to boil a small amount of water. This is all because of something called heat capacity. Before we get into detail, it is important to realize that there is differences between heat and temperature. Temperature is a way of describing how hot or cold an object is and measured in degrees Celsius, whereas heat is a form of energy and it's measured in joules. The more heat transferred to an object, the more its temperature will rise. So heat and temperature are related, but they are not the same. So what is heat capacity? The heat capacity of a substance is defined as the amount of heat required to raise the temperature of a material by 1 degree Celsius. However, what's more useful for us to think about the specific heat capacity of the substance? This is, as it says in the name, a little bit more specific. It is the amount of heat required to raise 1 kilogram of a material by 1 degree Celsius. Different materials have different known specific heat capacities, but we aren't always given a table like this, so we need to know how to calculate specific heat capacities ourselves. We have this equation which can be written as symbols like this. The energy transferred is the heat energy absorbed or released. This equation can also be rearranged to work out the temperature change. Subtract the old temperature from a new temperature. Let's have a look at a problem. The energy transferred is this, the mass is this, and the temperature change is 10 degrees Celsius because 50 degrees Celsius minus 40 degrees Celsius. Using the rearranged equation substitute the value and we get a 128 joules per kilogram Celsius. So there we have it. To summarize, specific heat capacity is the amount of energy needed to raise 1 kilogram of a substance by 1 degree Celsius. It's helpful because it allows us to work out how much energy we need to heat up or cool down the substance to desired temperature. To calculate it, use the following equation. Now it's about specific latent heat. Solids have fixed position. In crystalline materials such as metals, they are arranged regularly. Though the atoms have fixed positions, they are not stationary, they are not still. They vibrate due to the thermal energy. If we raise the temperature of the material, the atoms vibrate much more. This is how the thermal energy is absorbed. If the temperature is raised further, the bonds between the atoms will be broken apart. The breaking apart of the bond is what happens when material melts. The breaking of these bonds requires a substantial amount of energy. Is this called the latent heat of melting? Well, latent heat is used because it seems to be a hidden amount of energy. It's energy which does not raise the temperature of the material. It just changes the solid to a liquid. Once the bonds are broken, the atoms or small groups of atoms which are molecules move around randomly. They may take up a little more space, but the increase in volume is likely to be small. The atoms are held together by a mutual attractions. If we continue to heat the liquid, the molecules will move around faster and faster. Some molecules will have enough energy to break free of the bonds and move away. This is evaporation. At the point where a very large number of molecules have sufficient energy to break the bonds of mutual attraction, the liquid is boiling. The energy required for the molecules to pull away from each other against these attraction forces is considerable, as is the energy to push away the atmosphere that surrounds the liquid. Total energy required to change a liquid into a gas is called the latent heat of vaporization. We can use a very simple experimental demonstration to the latent heat of vaporization of water. We make sure the water in the kettle is boiling under the wall of the kettle is hot. We quickly transfer the kettle to a digital balance and measure the mass. You can see here 1.7 under 60 kilograms. Quickly transferring the kettle back to its stand, we switch it on and hold on the trip switch so that continue to boil. The power consumption varies, but I estimate the average 2640 watts. The power consumption is measured on watt meter, which is monitored by a separate camera. Gas continues to boil for a minute. The vapor escaping into the atmosphere at the end of the minute. We let the kettle switch off, transfer it back to the digital balance and measure the mass once more. As you can see, it's fallen to 1.656 kilograms. Using the values that we took during the experiment, my estimated value of the power was 2640 watts. The energy provided in 60 seconds will be 60 times 2640 under 58,400 joules. Subtracting the final mass from the initial mass gives us the 0.060 kilograms of liquid water converted to vapor. The latent heat of the material is expressed as the amount of the energy required to convert 1 kilogram from one state to another. Therefore, we need to divide the total energy we supplied by the mass evaporated. The value we calculated, 2.64 times 10 to the 6 joules per kilogram, is significantly higher than the generally accepted value of 2.26 times 10 to the 6. We would have improved our accuracy if we didn't prevent heat loss by other means, for example by lighting the kettle to avoid heat loss by conduction.
Heat is the flow of energy from a high temperature to a low temperature. When these temperatures balances out, heat stops flowing. Then the system is said to be in thermal equilibrium. The zero law of thermodynamics uses thermal equilibrium to define how two different systems can be said to be at the same temperature. For example, when molten rock comes up from a volcano, it will give off heat to the atmosphere until the rock and atmosphere are at same temperature. All systems tend towards the equilibrium over time, and some systems will take a lot longer than others. Knowing that, interacting systems will tend towards the same temperature, which allows for important application in all areas of science. For instance, the specific heat capacity of a substance can be determined by placing it in water and measuring the temperature after a period time. Zero law of thermodynamics also stated that if two systems A and B are in thermal equilibrium with the third system C, then A and C are in thermal equilibrium with each other. For example, a hot cup of coffee loses heat to surrounding and a cold glass of soft drink absorbs heat from surrounding. The first law states that energy cannot be created or destroyed but can be converted. So, this shows that thermal equilibrium obeys the zero law of thermodynamics. The relation of thermal equilibrium is an instance of a contact equilibrium between two bodies, which means that it refers to transfer through a selectively permeable partition, which is the contact path. Besides that, thermal properties are classified into two, which is the heat capacity or latent heat. Specific heat capacity is the amount of energy required to change the temperature of 1 kg of certain substance by 1 degree Celsius. This can be calculated using Q equals to mc delta T. Q refers to the energy absorbed or released, m is the mass of substance, C is the heat capacity, and delta T is the change in temperature. Specific latent heat is the amount of energy required by 1 kg of substance to change its state. This can be calculated using Q equals to mL, where Q is energy absorbed or released, M is the mass, and L is the specific latent heat. The sample of a heat capacity in real life is on a hot day at the beach when the bright sun is shining on everything you see, that the sand you stand on is very hot, yet the water is cold. This is because water has a high specific latent heat, therefore it is very hard to change its temperature, while the sand has a relatively low specific heat. Next is the example for latent heat. When the water is kept boiling, the temperature remains at 100 degrees Celsius until the last drop evaporates, because all the heat being added to the liquid is absorbed as latent heat of vaporization and carried away by vapor molecules.